Um, so I sent an email out last week, right? There was no review session yesterday because we had a holiday yesterday, so it's going to be tomorrow, right? So the first review session will be tomorrow at 5 p.m. in SC 319A, the same place it was last semester, for those who came last semester. And I'm still finalizing the hours in my TA, but actually my TA will have tutoring tomorrow afternoon, so I'm going to make an announcement tonight when that is and what room it is in, and I'll update everything tomorrow because I'm still finalizing everything, the syllabus and the calendar and the schedule and everything. So for those who didn't have me before, at the end of this week there's going to be another homework. When the first homework is due, I'm going to post a homework solution, and there'll be a quiz, right? So that's a new thing this week for those that didn't have it before. I'll probably post a quiz on Saturday. It'll probably be due on Tuesday night, so you have a few days to do it. But like I said, quiz 1 will be on what we did last week, which is basically electric force and homework 1, right? So that's what quiz 1 will be on. So it'll be posted on Saturday with another homework posted on Friday. And I think that's about it. So I need to post the PowerPoint. There's a foot. Let me just say one more thing. So there's a foot video that I posted on Friday, and it continued talking about electric fields, more complicated cases of electric field. So I need to post that PowerPoint. I'm going to post that tonight when I post the notes for today, right? So it'll be posted tonight. Yeah.
Will you be posting a homework video that you did last week?
Yeah. So the review session.
That's what
Yeah. Mm-hmm. Yep. Okay, so we're gonna go on from what we were doing last week. Anyway, so what we were doing last week is the electric field of a single point charge, right? We just started talking about it, and we said, okay, so suppose you have a single point charge. How do you calculate the field at some point around it? So in the example that we did last Thursday, we had a negative point charge. We picked 2 different points. One was kind of simple, and one was kind of more complicated. But nonetheless, you could figure out the electric field vector at both points, both how much it is and what direction it points, and writing it as a vector. So then, if you watch the flip video, which you should watch, and look at the notes associated with the flip video, we did, first of all, we did a positive charge, how it works if you have one positive charge. So the basic idea for electric fields is that they go away from positive charges, right, always, and they go towards negative charges, always. And then in the flip video, we did more complicated cases, which was if you have more than 2 charges. So I'm not going to go over the whole thing because that's the point of the flip video, but I'll just give you the highlights of what we did in the flip video. So suppose you have more than 1 charge. The question would then be, well, how do you calculate the electric field if you have more than 1 charge? Well, it's basically the same thing as more than 2 charges for electric force. So suppose you have 2 charges, a positive and negative charge, and you're asked, what is the total field at this point P? That's the question. What's the total field? So what you do is you calculate the field from Q1, like we basically did last Thursday. You connect them with a straight line, and then the field goes away from it because it's positive, and you figure out what E1 is, the x and y parts of E1. And then you do the same thing for Q2. You connect the point with Q2, and it's a negative charge, so the field goes towards it. Then you figure out what E2 is, the x and y parts of E2. And then the total field at this point is E, is just the vector sum of E1 and E2. So that's what you do, and that's what we did in the flip video. A couple of examples of cases like this. We're going to do another case today, too. But before we get to the example, the other thing, another point that we talked about in the flip video is also pretty important. We'll do some more examples of this today as well, is the relationship between electric field and electric force. So what this means is if you take a charge and you put it at a position where you know the electric force already, either because you calculated it or it's given to you, the electric field that is, you can easily find the force on the charge because of the definition of electric field. You can find the force, it's Q times E. So basically the amount of the force is just the absolute value of Q times the field at that point. And then the direction is, if it's a positive charge, the force and the field are always in the same direction for positive charges. And for negative charges, it's they're always in opposite direction, right? For a negative charge electric field. So the point is, you can either be given an electric field, just given to you as part of the given information and asked to find the force on a charge in that field, or you can calculate it. So for instance, in the flip video, we found the total field at a certain point in space from, say, 2 charges. Then you put a third charge at that point, right? And the force on that third charge is the field from that charge, from these 2 charges, sorry, times the charge. We did that in the flip notes, in the flip video, right? So that's the point. So those are the 2 main things we did in the flip video. So we're going to do 2 more examples. Well, another example, calculating the total electric field, or something to do with total electric field. I'm going to do other things with electric force and field after we do that. Okay, so let's go to the notes here. So I'm going to cheat a bit because I did this in the other class just a few hours ago. So I'm going to borrow the sketch from the other class since it's already done. Okay, so I'll give you a second to copy it down while I'm explaining it. Did I not copy it? Okay. All right, so this works. All right. Well, I don't need the 12 pin there. Oh, whatever. Okay, I'll get rid of that later. All right. So the example is this. So you have 2 charges. Oh, the charge didn't copy. This is Q2 is minus 2 microcoulomb. You have 2 charges on the x-axis, right? And we did problems like this in the flip video. We had 2 charges on the x-axis, and we figured out the field at different points on the x-axis. This is almost the same problem, except it's slightly different. So the question here is, you have 2 charges on the x-axis. One of them is positive, one of them is negative. You know where they are. One's at 0, and one's at x equals 0.2 meters, positive 0.2 meters. And instead of asking what is the total field at some point on the x-axis, like we did in the flip video, the question here is, where is the total field 0 besides infinitely far away? Okay, so there's 2 answers here. One is an answer we're going to calculate, and 2 is if you're infinitely far away from these 2 charges. And the reason why the field is 0 if you're infinitely far away is because the electric field is kq over r squared, right? So the further you get from each charge, the less and less the field gets. Particularly if you're really far away, basically infinitely far away, the field from each one is 0, and the total field is 0. So that's technically an answer, but we're not going to talk about that case. We're going to talk about at some point other than infinity, some point on the x-axis here, where is the total field equal to 0? That's the question, right? So does everyone understand the question before we do it? Okay, so whenever this is the question, where is the total electric field 0? There's this sort of recipe we can do each time we have a question like this, right? So let's see how we do this. Okay, first, this is where you start with all the time. Divide the, what did I say here? Divide the axis into 3 regions. That's probably not the best way to say that. But what I'm saying here, there's a place that's to the left of both charges, there's a place in the middle of both charges, and there's a place to the right of both charges. Those are the 3 regions that I'm talking about. So I'm going to borrow this sketch from the other class 2, because I did it already. Oops. So it looks like this, right? All right. So the rest of it I'm going to do step by step with you. Because it's important to see how it goes step by step. But this part I can copy, right? So what I did is I draw a vertical line at x equals 0, another one at x equals 0.2 meters, and the region to the left of them I call 1. You can call it whatever you want, but I just went from left to right and call this region 1, where it's to the left of both charges, and in the middle is region 2, which is in between both charges, and to the right of both of them, over here, is region 3, right? So that's where you start all these total electric field equals 0 questions. All right, so does everyone have this so far? Okay, so hopefully everyone has that, because I can't tell. All right, so then the next thing you do is you basically sketch the electric field produced by each charge in each region. So basically there are two charges. So in each region, 1, 2, and 3, you want to figure out what is the directional electric field produced by charge 1, and then we want to do the same thing for charge 2. So basically we're going to draw 6 different electric field vectors, 3 for each charge in each region, right? There are 3 regions and there are 2 charges, so it's 6 altogether. So let's do that. All right, so these are really on the x-axis, right? But if you draw everything on the x-axis, it gets kind of messy and you can't really tell what's going on. So I'm going to draw them not quite on the x-axis, so it's easier to see. All right, so what we're going to do is, there's 2 ways to do it. Either you can do each charge in each region, or you can just focus on one charge and draw the field in each region, and then focus on the other charge and draw the field in each region, which is the way I'm going to do it, right? So in other words, what I'm going to do is focus on just the first charge, the positive charge, and figure out what is the field in region 1 due to that charge, region 2 and region 3 due to that charge. So I did this for the other class. They seem to work pretty well. So I'm going to draw a little sketch beneath charge 1 to show you how you figure this out. So charge 1 is what? Positive or negative? Positive, right? So which way does the field go for a positive charge? Does anyone know? I mentioned it before. No. It goes away from a positive charge, right? The field goes away from a positive charge. So here's the positive charge, right? So this is just a little sketch to help with the to visualize the field around the positive charge, right? So the field goes away, right, in all directions. So it looks like this. When you're sketching it out, it was in the PowerPoint I showed you, but it goes like this, right? It goes just away. I mean, in every single direction, right? I'm just going to draw a few directions here, but the point is it just goes away, right? Okay, so the point is we're focusing on the x-axis, which is basically if you're either to the right or the left of the charge, right? Because region 1 is to the left of the charge, this charge. Region 2 and 3 are to the right of that charge, right? So if you're anywhere, it doesn't matter if you're region 2 or region 3, if you're anywhere to the right of that positive charge, which way do you think the field is going? Yeah, anywhere to the right, it's going away from the positive charge, which is to the right, positive x direction, correct? What about if you're anywhere to the left of that charge? It goes to the left, basically, in the negative x direction. So if you're just talking about charge 1, if you sketch the vectors, the electric field vectors, all I care is the direction right now. I don't care about the magnitude of it. So technically, this isn't a scale. I'm just sketching the direction. What I mean by that is if you go further away from the charge, the field gets smaller, right? So the vector should be getting shorter. But I don't really care about the magnitude. All I care about is the direction right now. So for charge 1, I'll just pick a random color here. Okay, so charge 1, the field anywhere to the left of it, which is region 1 is to the left, goes to the left. So this represents the field for charge 1 in region 1. And then anywhere to the right, it doesn't matter if it's region 2 or region 3, all it matters is that you're to the right of charge 1. The field goes the other way, in the positive x direction. So once again, these vectors aren't just scale. I don't care about the length of the vectors. All I care about is the direction. So E1's like that in region 2, the field from charge 1 in region 2, and the same thing in charge 3. Now, a point that I find I get a lot of questions about from semester to semester is people get a little confused with region 3 because there's a charge, right? I mean, if you're somewhere in region 3 over here, charge 2 is between this point and this charge 1. But we're just looking at this as if charge 2 isn't even there, right? All we're saying is, suppose you're just looking at charge 1. It doesn't matter. As long as you're to the right of charge 1, the field's in the positive x direction. So that's region 2 or region 3. Don't worry about charge 2, right? Don't worry about it being there, right? So does everyone get that for the field just from charge 1 in each one of the 3 regions? So now we're going to do the same thing for charge 2. In other words, if charge 1 isn't there, and you're only looking at charge 2, how does the field look like for charge 2? Which is what? Is it positive or negative? Negative. So let's sketch, like we did here for the positive charge, what it looks like. The field looks like for a negative charge, right? So I'm just going to draw a little negative charge here, right? So how does it look for a negative charge, the field, do you think? It goes towards it, in all directions, towards it. So I'm going to draw a few vectors like I drew before. You know, it goes this way towards it. It goes this way towards it. But specifically to the right, to the left of it, it goes like this. To the right of it, it goes like that, right? Towards it, right? It's just because the test charge is positive, which defines the field. Don't worry about it. Or look at, just remember, positive goes away and negative goes towards it. Okay. Right? That's the thing to remember. Yeah.
For the second part, E1, vector E1, why is it going in the direction, not in?
For this one?
Yes.
Why is it in this direction?
Yes.
Because it's away. Sorry, I started choking. Sorry. I ate something before class and now it's stuck in my throat. Because it's away from the positive charge, right? Right? So it goes away from it. Right? So if you're anywhere to the right, it's away, which is to the right. Okay, so once again, if you're anywhere to the right of a negative charge, which way does the electric field go? To the left, right? If you're anywhere to the left of a negative charge, which way does the field go? To the right. So in region 3, you're to the left, so you're going towards this negative charge. All right, so it looks like this. Yeah, I'm just picking a random color. Let's pick this color. All right, so for region 3, for charge 2, once again, these are really on the x-axis, but it's really hard to see if you draw them both on the x-axis, so just draw them below and above the x-axis. But that's the field for charge 2 in region 3, and then charge 2 and charge 1 are both to the left of charge 2. So therefore, the field is towards it, right? Like this. Oops. So the green is the field just from charge 2 in all 3 regions, right? All right, so everyone have this so far, right? All right, so that's the second step, is to sketch the field, produce the direction of the field for each of the charges in each of the three regions. Okay, so the next step, third step, I'm going to copy this again. So the next step is to third, identify the region or regions, there could be more than one, where the field, electric field, could be 0. So let's think about this. All right, so this just builds off what you did in the last step, but I'm doing it step by step, so it's easier, a little bit easier to follow. All right. So so you have these two electric field vectors, right? Produced by charge 1 and charge 2. So what do you think has to be true for the total field to be 0? If you add those two vectors up, in order for them to be equal to 0, what has to be true about the directions of one of them relative to the other one? They have to be in opposite directions, right? So if they're in the same direction, there's no way the field could be 0 because they just add together, right? So region 2, right, they're both going in the same direction, right? In the positive x direction. So they just add together and you get some positive field in the positive x direction. But in region 1, right, they're in opposite directions. In region 3, they're in opposite directions, right? So in this case, there are two regions where the field could be 0. So when you do this all the time, at least for the problems that we're doing in this class, there's one of two answers. You either get two regions that could be 0 or one region that could be 0, right? If it's one region, it's really easy. If it's two regions, then you have to think about it a little bit more. In this case here, there's two regions, so you have to think about it a little bit more, right? So the next part, actually part 3b, this is sort of part 3a, the third part, the first part of the third part. There's kind of the second part of the third part. If there are two regions, you have to figure out which region is the region where the field is 0. So it's actually not two different places. Only one of these places is the field 0. It's either region 1 or region 3, but it's not both 1 and 3. So you have to figure out which one is it. Is it 1 or 3? Does anyone know how you would figure this out? If it's region 1 or region 3?
Q times E.
Well, okay, so in order for the field to be 0, two things have to be true. One is that they have to be in opposite directions, right? You figure that out. The other part is what has to be the relationship between the amounts of the field, do you think? Right. So if E1 and E2 are the same amount, but in the opposite directions, then they cancel out, right? That's another thing I have to get to. So if you're in region 1, let's think about this. So what is the equation for electric field, by the way, before we get to this? Does anyone remember what the field for the magnitude of electric field is? What we did last week in the flip video. Anyone remember? We did do it before. KQ over R squared, right? K absolute value of Q over R squared. Okay, so this Q, the field here, E1, is KQ1 over R squared. So if you're some point over here, right, you're picking up random point on the x-axis in region 1. You're really close to this charge, right? And you're far away from this charge, right? So what's the field like from Q1 here? Is it going to be a big number or a small number, do you think? You're close to it, right? So what do you think the field is going to be, big or small? Big, it's going to be big. And Q1 is big, right? Compared to Q2, right? The absolute value of Q1 is big compared to Q2. All right. So if you're far away from Q2, when you're over here, you're far away from Q2, right? So do you think the field from the second charge is going to be big or small? There. Small, really small. Can it ever be equal to what the field is from Q1 at that point in region 1? Do you think? No, it can't. Does anyone know why it can't? Because you're close to a big charge, right? How can this field ever be as much as, how can E2 be as much as E1 when you're really far away from that negative, smaller charge, right? It could never be, right? So the idea is if there's two regions, right? The only one that works is if you're closer to the smaller absolute value or magnitude of the charge, right? So it has to be region 3, right? By process of elimination. But the reason why it's region 3 is because you have to be closer to the smaller absolute value of the charge, right? So that's like part 3b. If there are two regions, right? If there are two regions, the only place the total electric field can be 0 is closer to the smaller magnitude of charge, or absolute. So magnitude is the same thing as absolute value of the charge, right? If you only care about how much the charge is, not the sign of the charge, you're taking the absolute value. It's the same thing as the magnitude, right? Or absolute value of charge. So for this example, right, depends on the example, but for this example, it's region 3, right? Okay, so we established that it has to be somewhere in region 3, right? So now we're going to actually finish the problem and do the math in the 4th step. So the 4th step is this. Pick a random point somewhere in the region where the electric field is 0, and equate the magnitudes of electric fields in that region. So let me show you what I mean by that. Okay, so we've done all this work. It's a lot of work so far. But when you follow all this, we've established that the only place it can be 0 is in region 3, right? So what I want to do is pick some random point in region 3, in this case on the x-axis, and find the field of E1 and E2 at that point. So you pick some random point. It doesn't matter where you pick it. That's the point. You're trying to figure out exactly where it is. So you pick this point here, right? Just put an X down somewhere in region 3, which is to the right of both charges, and you call that P. In another class I called this variable X, but there's a slight problem when you do that, so I'm going to call it D in this class. It's not a big deal. In the other class they got it, but it just makes it a little bit easier to explain if you call this D and not X, right? So you call the distance from one of the charges to that point D or X, whatever you want to call it. But that's the thing we're trying to find. We're trying to find D, which is the distance, in this case, from Q2 to P, right? And that'll be where the field's 0. Okay, so once again, if the field's 0, that means that the amount of E1 is equal to the amount of E2, correct? Because if they're in opposite direction, they can't swap. So now what we got to do is figure out what is E2 here and what is E1. Let's look at E2 first. All right. So what is the equation for electric field again? So it's K times the charge, absolute value of the charge. So it'd be K times absolute value of Q2 divided by the distance from Q2 to whatever point we're trying to find the field at. So what would the distance be from Q2 to the point we're trying to find the field at? D, right? K absolute value of Q2 over D squared, right? So this here is KQ2 over D squared, right? That's the amount of the field for Q2. It obviously depends on D, but the point is we're trying to find D, right? Okay, so what is the... So for E1, it's the same sort of thing. It says it's KQ1, but it's divided by the distance between Q1 and this point squared, right? So what's the distance from Q1 all the way to this point P that we randomly picked over there? Is the distance between the charges, which is 0.2 meters, right? Plus D, right? That's the distance between them, right? So it's D plus 0.2 meters, right? That doesn't look good, but you get the idea, right? That's the general sort of equation. Now what we want to do is find D. That's the question. So what happens to the K's first? Yeah, doesn't depend on K, which is good, because that's a big number we have to worry about. All right, so then what we want to do is solve for D. So there's a bunch of math we have to do, right? But it's nothing more than some algebra. All right, so what I'm going to do is I'm going to cross multiply Q2 and D plus 0.2 meters squared. So when I do that, I get Q1 divided by Q2. And then I get D plus 0.2 meters squared over D squared. So it's just algebra. And then I can simplify the left-hand side and the right-hand side. So for instance, if I take the absolute value of Q2 and divide it by the absolute value of Q2, sorry, absolute value of Q1 divided by the absolute value of Q2. It's the same thing as taking Q1 and dividing it by Q2 and then taking the absolute value. It's the same thing. It doesn't matter how you do that. Now, on the right-hand side, both the numerator and the denominator is squared. So that means I can factor out the square, sort of, and what you get is this. Right? That's just a simplification that you can do. The good thing when you do this is, if you didn't do this step, you need to do the quadratic equation, which you could do. It would work on this problem. But this makes it easier to do. You don't have to do the quadratic equation. So then what we're going to do is we're going to solve for D. So we're going to get rid of the square on both sides. So how do you get rid of the square on the right-hand side? The square root, right? Now normally when you take a square root, it's plus or minus the square root, right? Because x squared is equal to a, x is plus or minus the square root of a, right? But when you're doing this, it turns out that you never need the negative answer. It's always the positive answer. It's just how it works out for these total electric field equals 0 problem. So when you do that, you don't worry about the negative. Just pay attention to the positive. Right? And then what you're going to do is solve for D. So you have to you have to multiply by D on both sides, so it's not in the denominator anymore. And when you do that, you get, well, I'll just write it again. All right, that's Q1 over Q2. You probably can't read it because it's getting messier and messier as I go. But D times the square root of the absolute value of Q1 divided by Q2 times D plus 0.2 meters. And then what you want to do is get everything with a D on one side of the equation. So I'm going to subtract D from both sides. So I'm going to cheat a little bit because, oops, I don't want to do that. So I subtract D and I get 0.2 meters, right? And then what you do is you factor out the D. So this is just a bunch of math, but it's kind of you know, a few steps. So when I factor out the D on the left-hand side, I get that. So then how do I find D? I get to divide by the thing in the parentheses, correct? So I'm going to cheat again because I already have this. Okay, so I'm going to move this here. So I get to divide by this. And then move this over. Anyway, so that's what you get, right? In the end. Okay, so normally what you do is you put in the charges in microcoulombs, right? So you normally convert to coulombs, which you write in times 10 to the minus 6, right? Let's see what happens when you don't write in, when you don't convert to coulombs. You leave it in microcoulombs, right? So you get 0.2 meters, and then Q1 divided by Q2. So this is the absolute value, right? So it's 5. So I'm leaving the microcoulombs here. 5 microcoulombs divided by 2 microcoulombs, square root. So as long as the units are the same, in other words, they're both in coulombs or microcoulombs, when you have a ratio of these two charges, the units cancel out, and it doesn't matter. You get the same answer. It's 5 halves, the square root of 5 halves, or whether you write it as coulombs or microcoulombs, right? It's always the square root of 5 halves. So you don't have to convert here. So it's the square root of 5 halves minus 1 in the denominator, and the numerator is 0.2. So you put that in your calculator, and you get, I think it's 0.34. Okay. So that's kind of the answer. But you probably want to specify a little bit more than this. All right, so let me explain what I'm talking about. So we just found D, which is 0.34 meters, right? So what is D in this picture here? D is the distance between Q2 and P. So you could say it's 0.34 meters to the right of Q2, right? But where would it be on the x-axis? In other words, this is x equals 0. This is x equals 0.2. So where exactly, if you're trying to specify exactly on the x-axis, where would it be? It's 0.2 plus 0.34, or 0.54 meters on the x-axis, right? That's probably the best way to say it, like exactly where it is on the x-axis. So the other way to say this, or the total electric field is 0 at 0.2 meters plus 0.34 meters equals 0.54 meters on the x-axis, right? Because then you know exactly where it is. You don't need to know where the charges are. You can just say, okay, it's 0.4, you know, if you look at 0.54 meters, that's where the total field is 0, right? Anyway, so that's how you do those types of problems. It's the same thing for every single type of problem where you're asked, where is the total electric field 0? It's this 4-step recipe all the time, right? You just set it up and do all these steps. Right? All right, is there any questions on that? Yeah.
I'm still a little confused when you were labeling the E1 and E2 vector forces versus field. I'm still a little confused about that. When you split up
The electric field, just the general?
Yeah, just when you broke it up into the 3 regions, and then like how you labeled like which ones were going which direction and how you did that. Sorry.
All right, so let me go back up to here, right?
Yeah.
So the idea is that the electric field for a positive charge, right, always goes away from it. For a negative charge, it goes towards it. So if the field for this positive charge just goes away on both sides, right? So to the right, which is here and here, goes to the right.
Right.
To the left, it goes to the left.
And then why is E2 different?
Because it's negative.
Oh, so it's just like positive and negative, and then like how those react to the points that you have there.
Yeah, you can think about it like that. It's not so much reacting. It's just that positive charges, the field goes away.
Okay.
Negative charge, it goes towards it.
Okay.
That's it.
Okay.
All right? Yeah. Right. Oh, I subtracted D from here to here. I just subtracted D. Right? Any other questions? Yeah.
I'm still kind of confused on how you decided it was region 3.
Because it's 1 or 3, so hopefully that makes sense. But you can't be close to a big charge because the field produced by a big charge, if you're close to it, is huge. It will never equal the field
Because
from the other
-2
charge.
is closer to 0 than 5 is.
No. So it's the smaller absolute value is the way you think about it. Q2 has an absolute value
Okay.
of 2. Q1 has an absolute value of 5, right? All right, any other questions? Okay, so the next thing I'm going to talk about is sort of a conceptual thing. It's telling you another class. So unless the lab has changed, which I don't think it has, the first lab that you do this week will be actually, if you're taking the lab, is measuring this thing called electric potential, which we won't talk about for like 2 weeks or 3 weeks. By the way, no one is talking about it. No other class is talking about potential this week, so I don't know why they have this as the first lab all of that. But the other thing you're going to be calculating in the lab is electric fields, which you know, at least a little bit about. So you'll be finding the electric field of what's called a monopole or a single charge, what we did last week. If you just have a positive charge, what does electric field look like for a positive charge? We already did that. And the other thing you'll be, well, there's 2 more things you'll be doing, but one of the things you'll be talking about is what's called a dipole. So let me just explain what a dipole is and how you can sort of figure out what the electric field looks like for a dipole. Okay, so a dipole is 2 charges of equal magnitude, meaning they have the same absolute value, but opposite sign, separated by some distance. Right? So it's kind of like what we just did, except because they were opposite sign, but they weren't the same absolute value, right? I mean, one was 5 microcoulombs, one was minus 2 microcoulombs. So a dipole, the difference is they have the same absolute value. One's plus 5, one's minus 5. One's plus 2, one's minus 2, right? They have the same absolute value, just opposite signs. That's what defines this thing called a dipole. So what we're going to do is try to figure out how you sort of calculate or at least estimate what the electric field looks like for a dipole. Okay, so let me borrow this actually. This picture here. I'm going to just change this, so don't copy this directly. But so a dipole is pretty similar, except this is, so I'm going to get rid of this. All right. So, but it, you know, you could put both of them on the x-axis if you wanted to. All right. So this is, say, a positive charge. This is positive Q, this is minus Q, right? So they're the same amount, just opposite sign. Let me move this down a little bit. And then what we're trying to do here is just sort of figure out what is the field at a few different points around this dipole. So first of all, this dipole is separated, these 2 charges, which are the dipole, are separated by some distance, right? In the last example, it would be like 0.2 meters or whatever. Well, sorry, not 0.2 meters, D. D in general, right? D could be anything, just the distance between the charges. Okay, so then what I'm going to do is pick some random points and try to figure out what the electric field looks like, total electric field looks like, produced by these 2 charges, right? So I'm going to pick one point, say over here, kind of close to the, these are just random points, right? I'll show you how it works in general. But one point kind of close to the positive charge. One point exactly in between them, halfway in between them. It's supposed to be halfway. I don't know if it is. Probably move it over a little bit, but. And then one point kind of close to the negative charge, right? So the point in the middle is supposed to be halfway between them. If it looks like it, if it doesn't look like it's supposed to be. All right. So what I want to do is figure out what does the electric field kind of look like for these, just as a sketch, right? For these 3 points. Okay, so let's look at the positive charge first and figure out what the field looks like for the positive charge, right? So we're going to do them one at a time. Look at the positive charge, look at the negative charge. So how would you find the field for a positive charge at this point here, which is closest to this charge? You connect the point and the charge by a straight line, right? And which way does the field go for a positive charge? Does it go towards or away from a positive charge? Goes away, yes. And do you think the field's going to be pretty big there? Because you're close to that positive charge, right? So is the field big? Yeah. So I'm going to draw these things to scale now. So in other words, this vector should be pretty long, right, for the positive charge because you're close to it, right? All right, so you connect these. I'm not going to do the whole thing. I'm just sketching it. But you connect these with a straight line, right? Connect this point to this point, and the field would be like this, right? Straight away from it. This is just from the positive charge, right? That's all I'm doing now is the positive one. So E plus is the field from the positive one on the left. What about the field at this point, right? The one that's like kind of in the middle. You do the same thing, right? You connect them by a straight line, and then the field goes which way? Away from it, right? But the key thing here is the field bigger or smaller than it was at the first point? Smaller because you're further away, right? So the line's going to be a little bit shorter, right? So it looks like this, or the arrow, I should say, not the line. Arrow. Okay, so it's going to look like, all right, so connect these with a straight line. It should be a little bit shorter, right? And this is E plus again, just the positive charge. Okay, so what about here? It's the same thing, right? The same idea. But the key thing is the field here going to be smaller than these 2 points? Yeah, because you're further away. All right, so you connect these by a straight line. And this is going to be kind of small, right? Because you're pretty far away from it, right? So far, so good, right? Now we're going to do the negative charge. So I'm going to use a different color. It doesn't matter what color. Just so it's easier to follow. I'll use this color. Okay. So now we're going to do the negative charge. Let's go opposite. Let's start here, go to this point, and then that point, right? So suppose you start at this point, right? Which way does the field go for a negative charge? Towards it. It's going to be pretty long, right? Because you're pretty close to that charge, right? Sort of like this one, the first one. But you're going towards it. So it's like this. It doesn't matter if the field line goes through the charge. It's just starting at that point. How long is it, and where it ends doesn't really matter, right? All right, so that's the negative charge. Now, what does it look like at the point in the middle? You go straight towards that negative charge, right? Okay, but here's the thing. So if you're in the middle of both of these charges, what's the relationship between the field produced by the positive and negative charge? The amount of the field, do you think? You're right in the middle, right? You're equidistant to both charges, right? And the absolute values are the same, right? So what do you think is true about the magnitude of the field? It's the same. Not the same direction, but the same amount. So it looks like this. You know, you're just going towards this negative charge. But the point is, these 2 vectors are the same length when you're in the middle. Right? Okay, so what about the last one over here, the one to the left, way over there? It's for the negative charge. You go straight towards the negative charge, right? And what do you think? Is it big or small? Small, because you're far away from the negative charge, correct? Okay, so it's going to look kind of like this. This is just a sketch, right? I'm not doing it perfectly. Just to give you an idea. So those are the 3 vectors for each one of those charges, right? So the total field is the vector sum of those things, right? So do you remember how you graphically sketch the vector sum of the 2 vectors? If you know what the 2 vectors look like and you want to add them up? Does anyone remember that from Physics 1? You basically put one vector at the end of the other vector, right? And you draw a vector from where the first one starts or the last one ends. That gives you a pretty good idea, right? So if I put, I'm not going to do it, but if I put E, well, I could show you quick, and then I'll bring it back, right? So if I put this one at the end of this one, then draw an arrow from where this one starts to where the green one ends. That's the vector, right? That's the sketch of the vector, right? But I'm going to bring this back because it's too confusing, right, if I don't, right? So it looks like this. If you had a mental picture of what I just did here, the total field looks like this. Kind of like that, right? That's the total field. Not exactly, but you get the idea, you know, somewhere like that. Now, what about the middle? What do you think it looks like in the middle? So you have one going up and one going down, right? They have basically equal and opposite y parts, right? Because they're the same magnitude. And they're going up and down to sort of the same angles, right? So one has some positive y part, one has some negative y part, but they're the same amount. So what happens to them when you add them up to the y parts? They cancel out, and you just have a field going in the positive x direction, right? I mean, if you add these two together, just like I just described for this one, basically what you get is a total field that's just horizontal, right? That's what it looks like, right, in the middle. When you're in between them, the field's just in the positive x direction for this case here. And then for this one, you know, you put E minus at the end of E plus, and you get a field that looks like this when you sketch it, right? It's just a sketch, but it kind of looks like this. So that's just 3 points, right, for this dipole. But what you can do is pick a whole bunch of points. And when you do that, this is the typical sort of, so let me see if I can just copy this part here. Well, that's pretty good. So what you see, and what you see in your lab manual, or what you need to draw for your lab this week, when you do your lab, is you'll see something that looks like this, or you'll draw something that looks like this for dipole. So what this represents is basically the field at every single point, right? So it goes away from positive charges. Then I'll explain where this comes from, though. You see a picture like this a lot. You have a field that goes away from positive charges towards negative. It always goes towards negative. Oops. So it curves like this, and then there's usually a whole bunch of lines here, and I'm just going to draw a couple of them. And this is what the electric field lines look like around a dipole. And the question is, where does this come from? So if you look here, we measured a point. We kind of figured out what the field is at this point, and this point, which kind of corresponds to these points on this field line here. So this point in the middle, and this point over here, right? So these vectors that we found, this point, and this point, are basically tangent to these lines. So what I mean by that is this. If I go back and I kind of sketch these in here. So here, right? If I go tangent, just touch that line at that point. That's approximately what the field is at that particular point, right? And then if I draw the next point here, tangent here, see, tangent is horizontal. And then tangent at this point here is something that looks like this, right? Which is the 3 points that we figured out. So what I'm trying to say is, you usually see these weird electric field diagrams for these dipoles. And these pictures basically come from finding the electric field at all these like points all around the dipole and then connecting them with a straight line, right? And that's basically what these electric field lines come from, right? So that's the electric field of a dipole. And that's where it comes from, right? What we did there. It's just finding the electric field at each point, right? All right, are there any questions? Because it's break time. Actually, when you come back from the break, I'm going to show you something else related to dipoles. But you can take a break now. All right, let me show you something that's just maybe helps you see the electric field a little bit better. So what I have here is a sketch, or not a sketch, an actual calculation of the electric field for a positive charge, and then I'll show you a negative charge. So this is nothing new. You kind of seen this before. So in the middle here, you don't see the charge, but there's a positive charge, and the idea is for electric field is a positive. For a positive charge, the electric field just goes away from it, right? So these arrows just go away, basically, from it in all directions, right? So these would be electric fields at different points. Electric field at different point around the star. So it's big. These arrows are gigantic, as you can see, when you're close to the charge, because the field is big there, and when you get smaller when you get further away, the field gets smaller. So those little arrows get smaller. So that's how it looks like for a positive charge. This is how it looks for a negative charge, right? It just goes towards it. And this is how we're used to seeing the electric field, just in, say, the XY plane, right? Just on the plane, on the desk in front of you, you draw the field just as if it was only in one plane. But the thing you have to remember that we don't do that often in this class is that, wait, where is it? The electric field is actually a three-dimensional thing, right? We usually think about it in 2 dimensions. So what I mean by that is, if you have a positive charge, the electric field goes away from that charge in all directions, not just in the XY thing, all directions, right? So this would be the electric field of a positive charge, right? There's a positive charge in the middle, and the field just goes away from it in all directions, right? This is actually what the field looks like, even though we don't see it like that often in this class. For a negative charge, it obviously looks like that, right? The field always goes towards it for negative charges, right? But it is a three-dimensional thing, right? It's something you got to pay attention to. And if you're trying to look at the electric dipole, don't worry about that. It's kind of hard to draw. All right, let me see if I can zoom in on this thing. And it's not working. Other class will work. Oh, there it goes. So this is the electric field of the dipole. If I got to rotate it, so it looked like it did. Well, it's going really slow. It worked better in the other class. This is kind of how it looked. It's a little bit tilted. But here's the positive charge, right? The field goes away from the positive charge, and then it goes towards the negative charge, right? So here's the negative charge. So that's basically what it looks like, according to the example that we did in the notes before the class. But the thing is really in 3D, right? So this is what the dipole looks like in 3D, right? Because it's actually a three-dimensional field, even though we usually look at it in 2 dimensions, right? It's actually 3D. So I just wanted to point that out, that these fields are actually three-dimensional, not just two-dimensional. All right, so the next thing I want to do is go back to the PowerPoint and talk about something else related to electric field. And, I lost my touch. I have to get that back. Anyhow, so the next thing I want to talk about while I'm getting this out, I'll go to the next slide. If I can go to the next slide. Where is it? All right, so I have to wake my part of my computer back up. All right, so the next thing I want to talk about is uniform electric fields. So a uniform electric field is sort of like a constant electric field. What I mean by that is that if you have a thing called the uniform electric field, everywhere in space where this uniform electric field is, the field is the same, meaning it points in the same direction and it's the same amount, right? That's what defines a uniform electric field. So far, we don't know of anything that produce uniform electric fields. We'll learn about them later. All right, I'm back. So the reason why nothing that we know of produces a uniform electric field, because there's only a few things that we know of. Basically, either the electric field from a single charge or electric field from a bunch of little tiny point charges. If you're talking about a single charge, the field around it changes all the time. First of all, if you go closer to it or further away from it, the magnitude of the field changes, right? And then if you go at different places around it, the field points in different directions. So what I'm saying is that point charges don't produce uniform electric fields. And even if you have like a dipole or something like we've been, the examples we did today, the field's different at all different points. If you pick different points, you get different fields, different electric field vectors. So nothing that we know of to this point produces a uniform electric field, but I think Thursday we'll actually learn about things. There are two basic things which produce uniform electric fields. We'll talk about those on Thursday. But for now, what we're going to say is, okay, suppose we don't know what produces uniform electric field, but suppose we have a uniform electric field. It's given to us, right? The field's given. The question is, why is a uniform electric field special, and what can we do with uniform electric fields? Right. So the idea is if you have a uniform electric field and you put a charge in a uniform electric field, you can figure out the force acting on the charge by what we did in the flip video, and what we're going to do again today. You just take the charge and you multiply it times the field, and that gives you the electric force on the charge in this electric field. So you can find the magnitude of the field, and you can find the direction, the magnitude of the force is just absolute value of Q times E, you'll see that in a minute. And the direction of electric force is in the same direction as the field for positive charges and opposite directions for negative charges. But the point is you can easily find electric force on a charge in a uniform electric field. The reason why uniform electric fields are important is because if the field is uniform, meaning it's basically constant, right? So at every point in space, the electric field's the same. When you multiply that field by the charge, it means that the force is the same everywhere, right? So if you can think about the electric field as being constant at every single point, and the force on the charge is constant everywhere in space, right? So if the force is constant and doesn't change, and you're using Newton's second law or whatever to find the acceleration, basically force divided by mass, or something like force divided by mass. We'll see examples of this in a minute. What do you think is true about the acceleration if the force is constant? Acceleration is constant, right? It doesn't change. If the acceleration is constant, then what do you think you can do? So remember physics 1, right? The first 2 weeks of physics 1. What did you do in the first 2 weeks of physics 1? Anyone remember? Kinematics, 1D kinematics. What did you do in 1D kinematics? Constant acceleration equations, right? Cases where the acceleration is constant, what did you do? You found things like the velocity after some time, how far an object moved in some time, right? The same thing here. Because the acceleration is constant for uniform fields, you can then, I don't know what's going on here. There we go. You can then use constant acceleration equations that you use from physics 1 to calculate things like how far is the charge moved in some time, or what is the final velocity of the charge at the some time, or how long does it take for the charge to stop after some time, right? These are the things you can do with uniform electric fields, right? So we're going to do a couple examples in class of this sort of process of finding uniform electric fields, or given uniform electric fields, and finding things like this. All right, so I'm going to go back to the notes. Okay, so I'm going to go here. All right. So I'm going to cheat a bit again because I did it in the other class, and okay. So let me just copy this, and then I'll do all the work again, step by step. But I'm just going to copy the picture. All right. So the first one, I'll explain it. So you have a uniform electric field, right? So we don't know where these uniform electric fields come from just yet. We will know within probably one class where they come from. So we don't know where they come from, but suppose you're given an electric field, a uniform electric field. It's 5 times 10 to the 6 newtons per coulomb, and it's directed in the positive x direction. So that means everywhere in space, the field is 5 times 10 to the 6 newtons per coulomb, and it's always going in the positive x direction. So if I pick this point, it's 5 times 10 to the 6 newtons per coulomb in the positive x direction. If I pick this point, it's the same thing, right? Any point I pick, it's the same field, right? So how do you represent a uniform electric field? Well, everywhere the field is uniform. So you know, usually the notation or the convention for a uniform electric field is you just draw a few field lines, not just one. You draw like 2 or 3 of them. It doesn't really matter, but more than one, just to sort of represent that it's a uniform field like this. And you draw the lines sort of equally spaced if there's more than 2. So that's just how you draw a uniform electric field schematically. Okay, so this represents a uniform electric field. Then you have a point charge, which is here, of +2 microcoulombs with a certain mass. You put it in the field, right? So here's the charge in the field, somewhere in the field. And you can include the weight force, but for this case, to make it a little bit easier, we're going to ignore the weight force for this problem. So usually you include the weight force. If I tell you not to include the weight force, I'll say ignore the weight force. Otherwise, assume there is a weight force, right? But for this one, we're going to ignore it. So this is a sketch of the problem. And then the first question is, what is the magnitude of the electric force acting on this charge? Right? It's actually pretty easy to figure out. If you're given the electric field and the charge, it's just a very simple equation to figure out the amount of electric force. So let's figure this out. We actually did it in the flip video, sort of this kind of problem, for a different type of problem, but here we're doing it obviously for uniform electric fields. So if you put a charge in any field, it doesn't matter if it's uniform or non-uniform, in this case it's uniform. Any field though, you just take the charge and you multiply it, the absolute value of the charge, and you multiply it times the amount of the field, and that'll give you what the amount or the magnitude of electric force on that charge is. This always works for any field. Right? So you just put this in, right? So it's 2 times 10 to the -6 coulombs. And then the field was 5 times 10 to the 6th newtons per coulomb. So actually the coulombs cancel out, right? And you get units of newtons, is what you should get, right, for force. And actually the 10 to the 6th and the 10 to the -6 just make 1. So it's really just 2 times 5, which you can kind of do in your head, hopefully. 2 times 5 is 10, right? So that's the amount of the electric force on that charge when you put it in this uniform electric field. So wherever you put this charge, I could put it here, 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 anywhere. The amount of the force on that charge is 10 newtons, right? That's the point. Yes. So does everyone understand that, right? It's pretty easy to figure out the electric force if you know the field and the charge. All right, the next part, remember, force is a vector, and vector is 2 things. The amount, which we found, but we also have to find the direction. So the next part, it looks like the same question, but it's a slightly different question. So what is the electric force vector, right? Not the magnitude, meaning how much is it, in what direction does it go, on the point charge, on the chart, right? All right, so this is just something to remember for the homework and for the quizzes and for the test. There's 2 answers for this, right? 2 possible answers. It's either with the field or against the field. Same direction as the field or opposite direction of the field. So if it's positive, if you put a positive charge in an electric field, the idea is that the charge in the field, the force on that charge in the field are always in the same direction, always, if they're positive. If it's negative, they're in opposite directions, right? But this is a positive charge. So therefore, the electric force is in the exact same direction as the electric field for positive charges. So it works like this. So I'll call this Fe. Anyhow, it's pretty simple, right? They're both in the same direction. So that's it. You know what the direction is. It's positive x direction, the same as the field. So if you write the electric field vector down, it's plus 10 newtons, meaning in the positive x direction, right? Plus 10 newtons x, meaning it's in the positive x direction, right? And that's it. So that's how you find both the magnitude and the direction of the electric force on that charge, right? It's pretty straightforward, hopefully. All right, the next part is what is the acceleration of the charge? All right, so this is whenever you ask for, I don't know why I said that's part C. Right, it's part C, not A. But anyhow, whenever you're trying to find the acceleration, you know the force, right, which is what we just found. You're going to use Newton's second law, basically, right? So we're going to apply Newton's second law. In the x direction, there's only one force that's in the x direction. Nothing here is in the y direction. In the next example, we'll have a case where that's not true. There'll be something in the x and the y direction. So this is as simple as you can get because there's only one force, right? I mean, there's not more than one force. So, oops. So when you add up the forces, if you ignore the weight, because we're ignoring the weight, it's just plus 10 newtons, right? And you know, so there's only one force that has x component, which is the positive 10 newtons in the positive x direction. So that, what does that equal to? When you sum the forces, what does it equal? Right, ma. Right. So you could solve that equation for a. So it's technically positive, but anyhow, divided by 0.5 kilograms, so it's positive 20 meters per second squared. So basically, the acceleration on this charge, basically due to the electric force, is 20 meters per second in the positive x direction, right? Hopefully it's not too bad to understand where all this comes from. But the point is, because the force is constant, because the field's uniform, it means that the acceleration is constant, right? That's the whole point of this. So now we can start doing stuff that you did in Physics 1 with at the start of Physics 1, basically 1D kinematics with constant acceleration. So the next question is this: if the charge started from rest, move this over here, it's easier. If the charge started from rest, what is its velocity after it has traveled? Displacement of 20 centimeters in the positive x direction. All right. So for this, we're going to use a constant acceleration equation, 1D. Constant acceleration equation, because everything here is 1D, just in the x direction. So we have these equations from Physics 1. These will be on your equation sheet, by the way, for the first test. Vf is equal to V0 plus AT. You have this equation here. V0t plus, that's a plus, 1/2 AT squared. Another one is Vf squared is equal to V0 squared plus 2a delta x. All right, so what are these three equations, right? These are the three most used equations, by the way, Physics 1. So which one are we going to use? We don't have a time, so that narrows it down. What's the only one that doesn't have a time in it? The last one, right? Can we figure out what that one? It starts from rest, right? So what is V0? 0. And we know delta x, right? And we know a, because we found a. So we're going to use the last equation. And yeah, that. Okay, so V0 is 0 because it starts from rest, right? So you have Vf squared is equal to 2a delta x. So Vf is plus or minus the square root of 2a delta x. But it starts from rest and the acceleration is in the positive x direction. So it's never going to go in the negative x direction, right? So it's just always going in the positive x direction. Okay, so then we write in what these things are. So this is 2 from the last part. This was 20. And then what is delta x from the given here? So 20 centimeters, right? but do we ever write in the distance or displacement in centimeters? No, it's always meters, right? So you got to convert to meters. So this is 0.20 meters. Take the square root, and you get your answer, which is like 2 point something, 2.3, yeah. So it's positive, whatever. So it's always going, it's moving at 2.83 meters per second in the positive x direction. It's always going to be moving in the positive x direction. Right, so that's one example of something we can answer. Exactly how fast is the charge moving. Another thing we can ask is how long does it take to travel 20 centimeters in positive x direction if it started from rest, right? So there's two ways to answer this question. Actually, it's probably more than two ways to answer it. One way is to use your answer from the last part, which is fine if you're confident with your answer, right? If you're sure this is right, then you can use this to do the next step. But there's a better way to do it without using your answer for part D, in case part D is wrong, right? So suppose you're ignoring what VF is. You don't know what VF is. What is the best equation to use of these three if you don't want to use VF to find T? You have the second one, right? Because we know delta x, again, we know it starts from rest, and we're trying to find T, right? So we're going to use the second one. Once again, you can use your answer from part D. You'll get the same answer, but this is a better way to do it in case part D is wrong. Right? So V0 is 0. So this is just 1/2 AT squared is equal to delta x. So then you just solve this equation for T. So you multiply by 2, divide by A, and you're going to take the square root to get rid of the square, right, for the T. So once again, you want this in meters, and then A is 20. So this works out to be whatever it is. It's 0.14 seconds. So it's not that long. But it doesn't matter. The point is, these are just examples of using constant acceleration equations with electric force from uniform electric fields, right? So those are the types of new questions we can do now, right? With electric fields and force. All right, so we're going to do one more example today related to this of uniform fields. And then you can go. All right, let me cheat again because I kind of did it already in this class. You can see we're doing the same thing. Okay, so let me just copy this, and then I'll explain it if I can copy it. All right, so while you're writing it down, I'm trying to explain it, or don't write it down, just listen. You can print out the notes later. So here you have a uniform field again, right? So uniform is actually the same field as the last example. 5 times 10 to the 6 newtons per coulomb in the positive x direction. So you sketch it with just a few field lines, lines going in the arrows going in the positive x direction like last time. You put a negative charge on a string, and you put it in this field. So the charge actually swings to the left, right? So the question first is, why is it swinging to the left, do you think? Yeah, because for a negative charge, the force and the field are in opposite directions, right? So if the field's going to the right, the electric force on it's going to be going to the left for a negative charge. And we do have a negative charge in here of -2 microcoulombs. So it's going to swing to the left. And after a while, it'll stop moving and come to equilibrium, right, where it's just sitting there. and it'll swing up to some angle, which is theta. That's what I call here, theta. So the question is, what is that angle? That's what we're going to ask, right? What is that angle? We're including the weight, right? So normally you just include the weight, unless I say ignore it. But because in the last example we ignored the weight, I just want to make sure that we include it this time. So I say include the weight. When you're doing a homework problem or quiz, always assume there's a weight force, unless I say there isn't, right? I'll explicitly say ignore the weight force. Anyhow, so you include the weight force, and the mass is 1 kilogram. So the question is, what is the angle that it swings to, right? This is almost the same sort of question, although it's slightly different than we did last week. Last week we did 2 positive and negative charges, don't remember, but they're next to one another. One of them was on a string, right? And they swung up to some angle. We asked, what is the charge, right? What is Q? It's the same sort of problem, actually, except it's a little bit different. It's a uniform field. We're asking a different quantity. We're asking for the angle, not the charge itself. But it's the same setup. We set it up the same way as we set up the other problem. So does anyone remember what we did when we did it last week with the charge on the string? What's the first thing we do? Yeah, we have to sketch the forces, right? Acting on the charge. On the string, here there's only one charge, so it's on the charge, right? So sketch forces acting on the charge, which are exactly the same sort of forces that we did last week for the similar sort of problem. Okay, so if we include the weight, there are 3 forces, right? What are the 3 forces? Just like last week. Same forces. The weight, which goes which way? Down. 2 other ones, right? Tension, which goes along the rope away from the charge, right? Along the string. And then the electric force, which I already kind of explained. It's just the opposite of E, right? In the negative x direction. So let's sketch those. Let's see what that looks like. So it's the same sort of sketch as we had last week, right? There's only one little difference, which we'll see. So we had this down, that's the weight. We have the tension force going like this here. And you have the electric force. So this is the electric force, right? So remember, for negative charges, whoa, that's weird. For negative charges, the force and the field are always in opposite directions, right? Okay, so 2 of these are pretty easy to write down the components for. So let's do this first. So W only has a Y part, right? No X part, right? So Wx is 0. And Wy is minus mg, right? Because it's going in the negative direction, and the weight is mg, right? Mg going down, negative y. And then, of course, Fe is pretty straightforward. We don't know what Fe is right now, but the point is, we can figure it out. But the point is, all of it is in the negative x direction, right? So you can write the x part of Fe is minus Fe, and Fey is 0, right? It has no y part. Of course, the tension has an x and a y part to it, but it's exactly similar to what we did last week. So to get from the beginning of the tension to the end of it, we have to go up. So if I'm going up, is that a positive y part? I have to go to the right. So what is the x part? Positive or negative? Positive, right? So this is Ty. This is Tx. And how does this angle relate to the angle that I have sketched there, do you think? They're the same, right? We don't know that angle. We're trying to find it. But the point is they're the same, right? Those 2 angles. So we already established that the x and y parts are both positive, right? But in terms of sine and cosine, what is Tx? Is it sine or cosine? Right, because it's opposite, right? And Ty is cosine, because it's adjacent. So this is basically what we wrote down last week. Same sort of things. So Tx is positive T sine theta, and ty is positive t cosine theta. All right, so we have the x and y parts, or at least the equations for the x and y parts. And then what do? We add up the x parts, add up the y parts, right, and see what we get. So let's do them one at a time. So we're going to apply Newton's second law, this time in both directions, because there are two directions, x and y. All right, so let's do the x parts first. So it's pretty easy, right? You're just adding this and this and this, right? 0 plus minus fe plus t sine theta. Then what does that equal if it's in equilibrium? It's not moving. 0, right? So what do you get? If you add fe to both sides, you get this. All right, so how do we find fe, the amount of fe? We haven't figured that out yet. So what do you do? I mean, it's just like part A of the last problem, right? If you know the charge in the field, how do you find the amount of fe? Yeah, it's Q times E, right? Well, absolute value of Q times. Okay, so the question is, what is theta? So with this equation alone, can you find theta? No, because you don't know t. T isn't known initially, right? Unless you're given t, but we're not given t, right? So you know Q and E, but you don't know t or theta, right? So that's the problem, right? So you have to look in the y direction and see if you can figure something else out that you didn't know already. All right, so we're going to do the same thing that we just did here in the y direction. So we're going to add this plus this plus this, right? So it's minus mg plus 0 plus t cosine theta. It's equal to 0 too, because in both directions the acceleration is 0, right? In the x and y direction. So let's add mg to both sides because it's subtracted here, minus mg. So when I do that, I get t cosine theta is equal to mg. So there's a problem here. The one we did last week, we knew the angle, so you could find t as a number. In other words, you can just plug in the angle, plug in mass and gravity, and you get t as a number. Here you actually can't get it as a number, but you can get it as an equation. So if I solve this equation for t, which is basically what we did last week, because I was setting this up. I was doing the algebra for this problem last week, right? Okay. So what I did last week is I solved for t, right? And that gets sort of eliminates t, which is what we want to do. We want to get rid of t so that we only have theta left, right? This is exactly what I did last week, right? You take that t, you plug it in to the x equation, and you see what you get, right? So instead of writing t, I'm going to write this. Oops. Times sine theta, right, because there's a sine theta there, don't forget that, is equal to QE, right? And then what you do, which is exactly what I did last week, you take, instead of putting the cosine with the weight, you can put the cosine below the sine. It's the same thing. Basically what we're saying is the order of operations doesn't really matter, right, for multiplication and division. So what's sine divided by cosine? Tangent, right? So we get mg times the tangent of the angle, which is the left-hand side of what we did last week. Exactly the same thing. On the right side, we had Coulomb's law, right? Qk squared over r squared. But here we have q times e. It's a little bit different. And then what we can do is solve for theta, right? So the tangent of theta is just basically the ratio of electric force and weight, right? QE divided by mg. So what's theta? it's the inverse tangent of the ratio of the electric force divided by the weight. So what you get is this. So the amount of the force is the same as it was in the last problem, because this is the absolute value is 2 times 10 to the minus 6. This is 5 times 10 to the 6th. So that's 10 newtons. The numerator is 10 newtons again. Then the denominator is 1 kilogram, because that was the mass. So it's 10 divided by 9.81, which is about 1. It's a little bit bigger than 1. If it was 1 in the parentheses, the inverse tangent of 1 is 45 degrees. So it's actually pretty close to 45 degrees, but it's a little bit more because it's not quite 1. It's about 45.6 degrees, right? But the point is, you can do things that we did last week. Well, similar to what we did last week, with uniform electric fields too, right? All right. Does anyone have any questions on this? All right. So on Thursday, we're going to talk more about electric fields. We're going to talk about something called Gauss's law of electric flux. And we're going to, I think, start to talk about things which produce uniform electric fields, right? Which we haven't talked about yet. All right, so see you on Thursday or tomorrow at the review session.